Here is a list of people who contribute to the activity at SpinTech. And as far as the SpinTech work is concerned today, most of the work has been done by Lamprini Frangou, who is with us today, Pablo Merodio, and Guillaume Forestier, who is also at the workshop. And we also have some collaboration, mostly for theory and to have access to all kinds of samples. So I will, as an introduction, I will discuss some of the antiferromatic metals with the perspective of spin-dependent transport. So we've seen that antiferromatic metals are mostly manganese-based, and there is a possibility to switch from a metal containing a light element, like iron, to an alloy containing a heavier element, like platinum. And this really opens a multitude of options for the study of different spin-dependent mechanisms, like the spin penetration depths in antiferromagnets, so I will talk about that during the talk. The inverse spin Hall effect, so we had already talks about that. I will talk a little bit about that. And now I want also to focus on these two last columns, because at the end of the day, if you want to have a ferromagnet-free memory, the temperature threshold for the device function is the Néel temperature, which is the temperature for the magnetic phase transition between antiferromagnet to paramagnet. So hopefully there are some materials that have a bulk Néel temperature above room temperature. But at the end of the day, if you want to work with nano devices or with nanometric samples, then what counts is not the bulk Néel temperature, which is pretty well known for most materials, but what counts is the Néel temperature at finite sizes. And here we see that there is really a gap of knowledge as far as finite size effects on the Néel temperature are concerned. So why? It's because there are, to my knowledge, no versatile technique to measure this quantity, and I will talk about that, and I will show a technique to measure finite size effects on the Néel temperature. Well, finite size effect in itself, it doesn't mean much, but I would say it all depends on the bulk Néel temperature. So for iridium manganese or iron manganese, finite sizes start, I would say, between at 5 or 8 nanometers. So below 5 and 8 nanometers, there will be some finite size effects. I will skip this slide quite quickly. I will not enter into the details. The purpose of this slide is just to say that, okay, you know all that. There are some insulating antiferromagnetic materials. There are also lots of semiconducting and semi-metallic antiferromatic materials. And as far as finite size effects on the Néel temperature are concerned, there is also a gap of knowledge for all these materials. So at SpinTech, we focused on the study of the injection first and the absorption of a spin current in antiferromagnets. So we've got a spin current going in, and we want to know how much the interface filters the spin current. So we want to work out the interfacial spin mixing conductance. And when the spins went through, we want to work out how far they can propagate in the antiferromagnet. So we want to know more about the spin penetration depths. And eventually, we want to know more about the relaxation mechanisms that take place in the antiferromagnet. At the same time, we want to measure this critical temperature at the nanoscale. I will talk about that later. So to study these kind of things, we first need to create the spin current. And to do that, we need a third party, and we use the well-known spin pumping method. So here is our typical system. So you've seen this kind of system also for other purposes. So we have a third party, which is our nickel ion, the ferromagnet. It's 8 nanometers. That's our spin injector. And on the other side, we have our iridium manganese, which is our spin sink. This is the material that we want to study. For the order of magnitudes, we vary the thickness between 0 and 15 nanometers typically. And again, we put a copper spacer in between the two because we want to avoid direct exchange bias interaction at this stage to simplify the interpretation of the data. So as it was said before, copper, as far as the spin current is concerned, will be quite transparent because the spin penetration lengths in copper are the order of hundreds of nanometers or even microns. and here we are using a spacer of 3 nanometers. So basically we put our nickel ion at resonance. That creates a spin current, and this spin current is directly proportional to this effective spin mixing conductance that contains all the physics of the absorption by the interfaces and within our antiferromagnet. So experimentally, we want to measure or to have access to this effective spin mixing conductance. So to do that, we can do it in 2 different ways. Say in reflection, where we directly have a look at the nickel ion damping, or the nickel ion resonance, and in transmission, where we directly have a look at the spin to charge conversion in the antiferromagnet. So I will talk about, I will show some results in these 2 conditions, and I will start with this reflection. This is a typical measurement, so that's the absorption spectrum of our nickel ion, absorption as a function of the field for a fixed frequency. Experimentally, we don't measure this, but we measure this one, which is a derivative because we simply work with a lock-in detection. And we can extract or determine fairly easily the line width of this spectrum. And the line width is directly related to the damping of the ferromagnet, which itself contains, say, 2 terms. One, which is the intrinsic damping, and the other one, alpha P, which is the damping related to whatever is absorbed by the neighbors. And this damping, since it is related to whatever is absorbed by the neighbors, it is related to this effective spin mixing conductance. So in practice, if we have access to a series of spectrum like that, we measure the line widths, and we can work out the alpha pump and the absorption by our antiferromagnet. So we've used 2 different techniques. These techniques were also introduced earlier this week. So we've used a waveguide at room temperature, but the advantage of this waveguide is that it's a broadband coplanar waveguide, and we can work with variable frequencies. And this way we can work out the inhomogeneous broadening of our system. So this is a technical parameter. I'm not going to enter more into these details. We use also a cavity at a fixed frequency, but this time we can vary the temperature, and we will see in the talk that there is some interest in varying the temperature. So here is a typical experiment, result. That's the absorption as a function of the thickness of our antiferromagnetic alloys for 2 alloys, iridium manganese, open circles, and iron manganese, closed squares. So let's have a look at the iridium manganese. We see that the system absorbs the spins up to a certain level where it levels out. So it absorbs as much as it can, and then it levels out. So from this data, we can extract a parameter which we think is directly related to the spin penetration depth in our material. So for iridium manganese, we extract typical values of 0.7 nanometers, which is typical for a ferromagnet. And for iron manganese, we get 1.6 nanometer-ish, which is typical for a paramagnet. From this data, we wanted to try to discuss the relaxation mechanisms, because we thought that if you are ferromagnetic-like, the relaxation mechanism is more dephasing-like, and if you are in a paramagnet, you have more contribution from diffusions. But I mean, this is actually still under debate. From this data, we were also wondering if there is any influence from the magnetic order, because we know that we are certainly not antiferromagnetic all the way through these thicknesses. I mean, the thinnest layer are probably paramagnetic. At this stage, we also had the intuition that by varying the temperature, we could work out the Néel temperature. But we had this intuition simply because we thought that you would change the absorption mechanism by changing from an antiferromagnet to a paramagnet. So we will see further in the talk that it's possible to work out the Néel temperature, but the mechanism is different. So in the next slides, I am going to discuss this. But before that, I'd like to make a small parenthesis, because from this data, it's possible in some cases to extract the interfacial spin mixing conductance. So here I listed interfacial spin mixing conductance that were reported in the literature for interfaces with various antiferromagnets. Okay, I will not risk myself in over-interpreting this data, because I think the origin of the interfacial spin mixing conductance is very complicated. It has to do with the quality of the interface, probably with the electrical nature of the material, with the collinear or non-collinear spin structure. But at least at the end of the day, what you want is the largest spin mixing conductance possible. And as far as this is concerned, copper, iridium manganese, or copper iron manganese is doing the job quite recently. I'd like to stress out also that there is a lot going on interfacial engineering. So it's possible to have access to this parameter by spin pumping, but this parameter is very important even when you do some spin orbit torque switching or these kind of experiments. And there is a very nice paper, not from us, but it's a very nice one, where these people, they have added hafnium in between cobalt iron boron and platinum manganese, and they could increase the torque efficiency by a factor 10. So back to our spin penetration lengths. Okay, I'm not sure it's very easy to read this table, but these are spin penetration depths, which were measured for different kinds of antiferromagnetic materials by different kinds of techniques. So in this graph, I plotted the spin penetration depths as a function of 1 over the resistivity for the manganese-based alloys that were measured by the spin pumping method. Okay? So same metallic family and same measurement method. And well, apart from platinum manganese, which remains a mystery to me, these data points, they fall on a straight line. So this surely underlines the diffusive mechanisms or the importance of diffusive mechanisms in the determination of the spin penetration depths. There is a review about spin penetration depths, not in antiferromagnets, but in all kinds of different materials, that clearly explains the evolution of typical penetration depths and 1 over the resistivity. So to go a bit further, we've varied the temperature. So here are some experimental results where we show the absorption as a function of temperature for different iridium manganese thicknesses. So to ease the reading, the data are shifted vertically. And what is interesting here is that we can see a little bump, which we call delta alpha P, and which occurs at a given temperature. And this temperature actually depends on the thickness of our film. And there are some theory in the literature who deal with spin pumping and fluctuations of the magnetic order of the spin sink. So this theory say that at the magnetic phase transition, when the order fluctuates, you should have an enhancement of the spin conductance across the interface. So it's probably what we see. So transposed to our case, our alpha P is related to the interfacial spin mixing conductance, which itself is related to the dynamical susceptibility of our spin sink. And it has been shown during the workshop that and demonstrated before, that the susceptibility of an antiferromagnetic material shows a maximum at the critical temperature. So what we observe here, we think, is simply a signature of the magnetic susceptibility of our material. Just to make the things clear, this magnetic susceptibility does not correspond to this material. This is, I think this is one of the famous graphs. I mean, Aurélien Manchon likes very much this graph because it's one of the first graphs where susceptibility was reported. And And that was reported by one of the co-workers of Neil, which is BZ. So actually here, we are working out the magnetic susceptibility for ultra-thin films and for isolated films. So that's because we have access to a unique surface-sensitive tool, and to date, most techniques to determine the magnetic susceptibility are volume-sensitive. So I think we really have something here to dig further and to do some more fundamental, well, some experiments and dig further the fundamental things. Just to note that we have done this experiment and we have demonstrated this for metallic antiferromagnets, and pretty much at the same time, there are two other groups that reported similar conclusions for insulating antiferromagnets. So NEO and COO. So there was one group at the Johns Hopkins in the USA and one group in Tohoku in Japan. So from this, if we spot the critical temperature, we can plot the evolution of the critical temperature as a function of the thickness of our antiferromagnet. And these data points, they also fall on a straight line. And actually, there are some very simplistic models that describe the evolution of the critical temperature as a function of a material's thickness. This is a model by Zhang and Willis in 2001. And also, it is a very, very simple model. It proved quite robust for different kinds of ferromagnetic materials. So the model simply states that the critical temperature somehow should be related to the amount of interspin interactions. So whenever you remove one layer here, you remove some interspin interactions, and you should reduce your critical temperature. And this model can fit our data quite well. And from this, it's possible to extract a parameter that I think doesn't mean really much. It's a kind of effective spin-spin correlation length, but it doesn't mean much. Well, we can extract these kind of parameters. There were talks about critical exponents some days ago. This model is a model in the mean field approximation, so lambda equal to 1, I think. Our data also agree pretty well with what can be found in the literature to date, which is one data point. This is this one. And it's a data point that was measured by another group by calorimetry. Yes, this is the evolution of the critical temperature as a function of the different caps that we are putting. Actually, here we wanted to test two things. We wanted to see if the Néel temperature or the critical temperature is robust against its environment. And we thought that maybe if we add platinum or palladium that can get polarized, we could somehow gain one extra kind of polarized layer, and we could this way increase the Néel temperature. But it didn't work out very well. But the good conclusion is that the critical temperature seems to be robust against its environment. By knowing this effective spin-spin correlation lengths, and by using the same theory, or the same model, it's possible to extrapolate to thicker layers, and then we can plot the full phase diagram for iridium manganese. So critical temperature as a function of thickness. So on the left-hand side, we are paramagnetic. On the right-hand side, we are antiferromagnetic. And what's interesting here is the data point at room temperature, because the threshold for the magnetic phase transition at room temperature, the thickness threshold, is around, well, say 3 nanometers. So back to our initial data. Around 3 nanometers, we see that we have some data points which amplitude are exactly the same on the left side when you are paramagnetic, and on the right side where we are antiferromagnetic. So which means that in this particular case, for these particular samples, there is a limited influence of the magnetic order over the effect of the elements constituting the alloys. So it's probably because we are in, well, either because we don't see the effect of magnetic order in the noise here, or because we are highly polycrystalline and non-collinear. But despite that, because I don't want to finish this slide at least with a negative note, there are some practical use of polycrystalline antiferromagnets to get enhanced spin pumping, so enhanced spin sources, and to demonstrate this, a way to determine the nail temperature at finite sizes. I will spend 1 or 2 minutes to discuss some data in transmission, so where we have a look at the spin to charge conversion directly in the antiferromagnetic layer. So in principle, it's possible to have access to the same parameters, the interfacial spin mixing conductance, the spin penetration length, and in addition, as it was shown by Axel this morning, it's possible to have an idea of the amplitude of spin-orbit coupling by extracting the Hall angle, the spin Hall angle. So I'm just showing some results of the inverse spin Hall effect in iridium manganese. So that's the normalized charge current as a function of temperature, again for different thicknesses of iridium manganese. And in this graph, we see that we have a huge peak here in the graph, but this time this peak doesn't move with temperature. So somehow this peak hides what we want to see, which is the magnetic phase transition. And actually, the charge current, which is related to the spin current, is inversely proportional to the total damping of our nickel ion. And for nickel ion, this is the damping of our nickel ion, which shows a huge minimum here around 80, 100 Kelvin. And this huge minimum, of course, translates into a huge maximum here that doesn't move with the thickness of the antiferromagnet. This huge minimum is quite well understood in the literature, and this paper talks about that. So I won't say more about the inverse spin Hall effect because there has been already a lot said about that by Axel this morning. Yeah, this is the final slide. So I hope I've shown some use examples of studies of the spin injection and absorption in antiferromagnetic materials by the spin pumping method. It's a quite powerful method because it's possible to work out the interfacial spin mixing conductance and then to do some interfacial engineering that will be useful for many, many other experiments. It's possible to measure the spin penetration length. It's possible to measure the nail temperature and the magnetic susceptibility at the nanoscale. And if we think of it at the phase transition, you've got more spins that go through, so somehow you can use also the phase transition as to do some interfacial engineering as well. And it's possible to measure some spin orbit interactions with the inverse spin Hall effect detection. So with this, I thank you for attention.
Yeah, thank you very much. Other questions?
I think the slide 11 or 12 where you're showing the spin diffusion activity and the zero. And I just saw platinum manganese twice. One you said that this is a mystery, a low number. Then I thought I saw another.
It's
I think it was around 10.
Yes, this one. Yeah, there are lots.
No, in the graph. In the yeah, there's one on the line and then one you call the
It's probably a mistake. Probably a mistake, or it probably results from two different measurements from two different groups. I hadn't seen that yet. I'll have a further look.
And a good question. So I probably explained that. I just missed the point. You were not able to measure the nail temperature above 1.5 nanometers for some reason.
Yeah, this is yeah, in here. Actually, in this case, the amplitude of this delta alpha P seems to decrease when the temperature increases. So if we have a look at the theory by Onuma and his co-workers, there is a surface to volume preterm, prefactor, before the susceptibility. So in this case, when we increase the volume of our material by increasing the thickness, we reduce the amplitude of the peak. But
So you
okay.
lose the sensitivity at these higher
Yes, absolutely, yeah. Hopefully, I think in the same Onuma paper, they say that if you have a larger spin-orbit interactions, then you should have a peak which should be larger.
Further questions?
Actually, I'd like to add to that. You said that you have polycrystalline antiferromagnetic, and you speculate about changes or similarities, differences if you go to the actual single crystalline stones. Would anisotropy, for instance, be an important aspect? How would it change these?
Absolutely, yeah. So in this case, I would say that these kind of graphs don't really depend on the angle at which we measure. So I guess when you have a really epitaxial film and a collinear spin structure, there should be some angular dependence, for example. That could be one of the main differences, I guess.
So you're looking at sort of an average value?
I would think so, yeah, in this case, yeah.
Further questions?
And yeah, just to finish with that, maybe with your question, the fact that we are looking at somehow an average value, or it can be seen in this small increase here. I think there was a talk by Brian Gallagher some days ago, showing that, okay, in the susceptibility should be, you start from 0 and you go up. If you are parallel and if you are perpendicular, it's a straight line. And when you're a polycrystal, you are somewhere in between. So it's probably why we have this small increase here.
Any other questions or comments? Seems not to be the case.
Thank you very much.